Swayam Prabha. Digital India. Educated India.
So I hope all of you are convinced about why we do this business of stress and strain. It allows us to get one universal curve that describes the material behavior without drawing different curves for each dimensional specimen. If you do it very fat bar and you do it with a thin wire, then you will get different graphs. We can avoid it if it's the same material. We need to find out what is this failure point, at what point will something break. That also comes from experiments. Okay, for a given material, there will be some stress at which this material will fail. So for typically, you should get a feel for some materials. For typically what is called a mild steel, which is the very common material that we use. There are high strength steel, there are like soft steels and so on. Mild steels will have a typical failure strength of about 500 megapascals. I hope pascals you know, so megapascals, 510 to the 6 megapascals. Okay, so now you have enough information. You have enough information to tell me to design this wire which will support my car to hang from the ceiling of my garage. I have given you enough information for that. But before you do any calculations, I want you to guess what will be a appropriate thickness of a wire, steel wire with a 500 megapascals thing, which will support my car to allow it to hang from this. Is that diameter? Diameter is what you're asking? Radius. What is the diameter? Exactly, good point. What is the weight of the car? I didn't even answer that, but
diameter
2 centimeters.
Average weight which will be.
Okay. Average weight also you also guess. See, by the way, look at this table here. Just to get this table that all of you are sitting at. Look at the thickness of the legs. How many centimeters is that?
How much redundancy?
Sorry?
How much redundancy?
We'll see. You tell me with redundancy. 5 to 6 centimeters? 1 meter diameter. So, okay, we got one 2 centimeters from him, one 3 centimeters, one 1 meter. It's okay. See, lots of times I want you to first guess some number. Don't hesitate. Just guess. If you are very wrong, you will be kicking yourself. How come I was so wrong? Your ego will not
15 centimeters.
Whereas if you are correct, you're like, wow, I am the man. Okay, I am the greatest person. Right? Yeah.
On the table that you mostly follow, these tables.
Tabling. Still, but look at the now weight, not even few tens of kilograms. What will be the weight of a car? 1,000 kilos, we got one. Any number, any other number? Is it 100,000 kilograms? 2,000 kilos, 1,000 kilos. What, any other numbers? 1,500 kilos. What do you think? Not even that much. Tell me a number. 8,000. So we go from all the way from So you want to stick with the 100,000 kilograms? It's okay, we'll pretend you didn't say it. We'll pretend that you didn't say it. Anybody? What about you? What will be the weight of a car? 1,500 kgs, okay? 1,800. Wow, that's a very specific number. That's a very good. So, So good. So any other numbers? 500 kilograms. Okay. So by the way, yeah. It's okay. You tell me what type you think, and you tell me number. 8,000 plus or minus a few kgs. What is a few? 5? Okay, good. So very nice. I got a couple of nice, interesting answers. First is what kind of car? Okay, and I think that will actually does matter by a factor of. What do you think? What factor do you think it will affect? Depending on it will only affect by a few hundred kgs or by a factor of 3 or 4. Yeah. See, amongst cars also, my guess is there will be a range of maybe 3 or 4 weight range. Okay, even amongst what you would call a car. Forget about going to a truck and all that. Okay, but that's okay. So when I ask a question like this, and when you also have this thing, you should know that there is always going to be a range. And very nicely, she said 3,000 kgs plus or minus a few kgs. That's a very, I like a plus or minus always to any answer. Okay, what's your age? 18 plus or minus 5. That's good. Right? So, and you will be, of course, accurate, and you will not have said anything. So, as an engineer, you should always be aware that you can never say anything precisely. Okay, there's always going to be, and that's why certain things do bother me a lot. For example, what is the age of the universe? Has it 13 point? See, the 13.8 that bugs me a lot. That 0.8, what the hell is that 0.8? Where did that 0.8 come from? Is it plus or minus 10 years? Plus or minus 100 million years? Plus or minus 1 billion years? What is it? There has got to be some variation to the thing, and you're saying 13.8 means you're saying it's only plus or minus 0.1 billion years. And I don't know if that is good. Huh?
So maybe the error is after the 0.8. It's like 0.01
That's what.
plus or minus 0.02.
Correct. So usually if you say 13.8, it means that it's either plus or minus 0.05. That is usually what it is. But it's not believable. Okay. Anyway, let's go further. So anyway, the point is, so you can see this thing. So in such a case, when I get such a range of answers, my answer will be just the average of these. So I don't have to, I can be the most popular guy, right? Most popular teacher in that way.
So that it is
Okay. Good. So what will happen is, generally what we have to do is we have to take something that is reasonable and then put a factor of safety on it. That's what you are saying. So we'll come to it. So anyway, let us assume that it is say 2000 kilograms. Okay. So then what happens is, what we said was, when the stress reaches 500 megapascals, it will break, which means that if 20,000 newtons is applied over the area of the thickness of it, and that reaches 500 into 10 to the power 6. Okay, so this is newtons and this is pascals. So this should be in square meters. Okay, or if you want it to be in square millimeters, I can just remove this. Okay, so you can see now, what is it? 20,000 by 500, what is that? Okay, 40 millimeter squared, which if you take like if it's a square cross section, it's only 6 mm side or 7 mm side, let us say, will support a 2000 kilogram car from the ceiling. Is that surprising to you? Is this a case where you have to put up your hand and say, sir, that's bullshit? Yeah, good.
What is the hinge which the steel is attached to break on?
What if the
So you have to attach the steel somewhere onto the cables and all that. What if those things tear off?
they could break? Okay, but supposing those don't break, somebody make that really fat. Okay, it'll add another 100 kilograms, man. What is there? It'll have 100 kilograms. Okay, it's okay. Take it. Take it. I don't care. So, 7 mm side or radius also you can consider whatever. Side of a square of 7 mm, less than a centimeter, okay, 0.6, 0.7 mm is enough to support the weight of. So, where did we go wrong? Subconscious mind. Good one. I'm glad you're all paying attention. Good, very good, very good. So, yes, please.
So I think we just assumed the safety factor built in. We didn't necessarily consider what is the
Safety
minimum
factor of 2. That means square root of 2 multiplied by 0.7. It's 1 centimeter. So looks like it's actually close to this 2 centimeter radius that people got, but still you're off by factor of 3 or 4. Yeah.
Sir, since we thought like a car is a heavy object, our mind tends to go to a bigger value because it's a bigger car, though we know that it's.
But 0.7
inversely
mm is okay.
It's smaller compared to what we thought.
Okay. So he's agreeing to that 0.7 as a possible answer. Yes.
Sir, you sort of fooled us with the table example.
I purposely fooled you with the table example. Then why is the table leg so fat? It's hollow, but still, are you telling me that you won't say that this much thickness? Correct. So, yeah, let's go on forward. So, basically, actually, there is nothing wrong with this answer. It is true that literally a 0.7 mm side square wire can support a 2000 kilogram car. And some of the people got some hints about why don't we ever see that? Why do you see, even for this fan, this little, probably like 10 kilograms fan, you can see that shaft is quite thick. And you'll see that everywhere. You'll see like quite, even if this is not metal, you'll see them quite thick. Why is a question that you should really ask yourself. Looks less fragile, but you're willing to spend so much more money for it? No. So what happens is actually, this is only first one point is that actually, if you really see some of the say cables that are supporting, like part of your construction bridges and all that, considering the weight of those bridges, those cables are really quite thin. Okay, you literally see like 2 centimeter diameter cables, part of many cables. Of course, they're not only one cable, but so in other words, the strength of objects is actually quite high for this so-called static loading in which the forces does not change with time. Okay, actually speaking, that's why structures which last for 5,000 years are quite easy to build. If you just have just one load and you put something like that, most materials like your wooden blocks and like stone and all will support it quite a long time. Okay, so that has generally not been a problem. A problem comes where the load changes with time. Okay, so question?
Yes, how exactly are we considering a bridge to be statically loaded? Because we have traffic going over it, especially in peak hours, it could increase a lot.
Okay, so his question about, I said bridge which is statically loaded is not a problem, and he's worried about whether there's also a dynamic loading on the bridge. Okay, it's just the ratio of the static load to the dynamic load. The dynamic load component will be very small for these sort of structural objects compared to the static load. Even in buildings, even in a building like this, due to wind load, there will be some amount of, especially a high rise, there will be some swaying and there will be a fatigue, what's called a cyclic load. But static load is a dominant component. It's the one that works. So the point is, actually, people thought that they understood very well. So thin wire is able to support material. So when the first railway was built, the first rail was built, the axle of the railway thing, they designed it based on how much of the load of the thing. promptly within half a kilometer that thing broke. The axles all broke. Why? Because that is one of the first time where significant loading. I mean, of course, people were driving carts and all for a long time, but the loads were much lower than compared to the rails. So they thought they only just did a small static loading calculation, but literally, what happens is when you have a shaft of a car or a rail, it keeps going like this, and if you have a load, so it's bending like this, but when it rotates, now it's bending the other direction. So the same fiber, if you look at the top layer, it would be, when it's like this, it will be compressed, and that same fiber, when it goes there, it will become extended. So compression, extension, it happens, and that causes failure. So that is called fatigue. So far we looked at what is called static loading. Static loading is very well understood. Euler, Bernoulli, these are all people who come up with some nice models of materials which are under static loading. That is, you put a load on it and keep it like that. How much will it deform? Okay, and at what point will it break? These two questions perfectly well answered for fixed loads. Okay, but frankly, it's not such a difficult problem also. At the most, you can go to Calvin's dad example. You can keep putting more and more weight. When it breaks, you can build a slightly bigger one. Okay, so static load is not such a big problem. But I'm telling you right now, even now in 2023, things that are being dynamically loaded, constantly the load keeps changing, is actually very, very difficult to predict. We still don't have very good models. Okay, so dynamic loading. Dynamic means time dependent, leads to what is called fatigue, and it's very poorly understood right now. Literally, we are as bad as we were 150 years ago. Okay, so let me just explain how then we would solve this problem. And so what I do in my lab, I think somebody came and asked during the 5-minute break. So what kind of things do I do? I actually work on models of this. Okay, so why do current models, why don't they work? Why are they not very good? If you look at it, it is because of this small leap in faith that we did, going from this wire to this concept of stress. So what did we do when we say force per unit area? In our minds, there was a uniform distribution of material. So in other words, there was a continuous, in our minds, there was a continuous set of fibers. It is called the continuum hypothesis. So currently, we model all these materials as continuous bodies, where material is there at every point. But all of you know that's wrong, right? What is the alternative view of it? What are those discrete things called? No, not all the way to quantum, but somewhere between there. Molecules and atoms, right? So real bodies are actually composed of atoms. Okay, whereas but from the time of Euler, who wanted to, from the time of Hooke, actually Hooke did not do anything. Poor guy, he only wrote W versus this thing. But since time of Cauchy and Euler, they moved to this continuous distribution of body. But the problem with this continuous distribution is you cannot model any discontinuity. If you say something is continuous, suddenly you cannot introduce a discontinuity later. So there is a fundamental philosophical problem with that. And actually what happens is real life will have lots of defects. Real life will have small defects. There will be some small cracks inside and so on. And as you keep loading it, those cracks will keep growing, and eventually the thing fails. So we don't have a good way of modeling such processes. So I'll just give you a little hint about how we do it. I hope you will find it exciting because it's very fundamental. It's as whatever you know, you can still do it. So what we do is, supposing I have to model the cyclic loading of a beam. So supposing I have a bar and I'm doing a cyclic loading. I'm pulling it and pushing it and so on. A cyclic loading, fatigue loading. Question?
Yes, sir. So you said that we are modeling all the real life materials, assuming that they are to continue. Has this kind of modeling produced like significant errors in our calculation for which we have to overcompensate?
Yes, good question. So his question is this continuum modeling, which is by the way the modeling approach right now. Aircraft engines are produced like that. I mean, are designed using such approach, and everything, all the latest sophisticated stuff, people do that. But because you are not able to model the actual crack initiation and growth, you are having to overcompensate. So all things are over-designed. Not only over-designed, you finally don't know when the damn thing is going to break or not. It's just, you just don't know. Okay. So just to give you an idea, if I took this bar of little piece of chocolate, I mean it's a chalk, and pulled it, okay, and it broke, there will be a small, I said like plus or minus, there will be a small variation in the load for failure. There will be a small variation in the load for failure. That variation will be about plus or minus 5 to 10%. Okay. But the same thing, if I apply a dynamic or fatigue load, then we look at the number of cycles of such loading to failure. So if I look at the stress applied and the number of cycles to failure, so we get a curve that looks like this if you do the experiments. Do you know the variation in that? It could be a factor of 10. So at a given stress, a thing can fail in 1 million cycles, or it could even fail in 10 million cycles. Factor of 10. That means if you want it to be safe, you have to make it 20 times as thick because twice even the worst case scenario for it not to fail. So that is the consequence of the current approaches. Okay. So how are we doing on time? It's 3:35. So let me just outline, and maybe I'll have you also do some calculations that will help me in doing this failure calculation. Let's do a failure calculation. So what I do is something, so I don't do this complicated continuum modeling and all that. Okay. I'll go back to my 12th standard, 11th standard physics. So what I said was, you give me a bar and you're going to apply cyclic loading and it fails after 10 million cycles. Why does it do that? Okay. So I say it fails because there is some small crack somewhere. All materials will have, this is the fact of life. You produce your material as carefully as you want. It will have some small void, some air bubble will be there, some void, okay, something called dislocation will be there, some defects, some particles will come and sit there. There will be some defects. That's a fact of life. Okay. And right now, we do not, the current sophisticated modeling approaches do not consider that. So what I said was, then why do we do that? Let us do a simpler model. So, and I want all of you to help me out with this calculation. It's very simple. So what I do is, I'll say, I'm going to model this bar as a bunch of parallel springs. So I just put some 5 or 6 parallel springs. Of course, I can make it more and more parallel springs to make it more sophisticated. Then I'll have to use a computer to solve it. But you'll understand the concept with even 2 parallel springs. So let's just do 2. So by the way, you all done parallel springs in your school already. That's it. That's all we're going to do. Awesome, no? So what I'm going to do first is, okay, I have to introduce one more concept, sorry, or maybe not, let's see. We can do it even without that. I want to first I want to calculate the load deformation response, the load deflection response. Don't worry about fatigue loading yet, just a single load, okay. For this two spring model, where each of these springs has a, so this spring is one which has a crack in it. You remember I said there's a crack here. So this entire region, okay. So this entire region I'm modeling as one spring. So the spring is a bit weaker than the spring where there's no crack. So what I'm saying is, I'm going to model this entire bar as just two springs, but the thing is, each of these springs will have slightly different K1, K2 and failure strength, failure load F1 and the failure load F2. You understand? So in other words, what I have done is, so imagine this chalk piece is there, okay. If I am going to pull this chalk piece, it's going to break somewhere. Where will it break? If I take 10 pieces of chalk and pull it, will everything break only in the same spot? No. One will break in one location, slightly another location, there will be some small variations, right? You've seen that. Why? Because the chalk piece will have some defects, some voids, some pre-existing cracks, which are slightly different in each of those. So what I'm doing is, I'm going to model this bar as a bunch of parallel, in this case only two, because 2 is easy to do, two parallel springs, each of them has slightly different properties. So this is a very fundamental innovation in looking at it, because now it allows you to model the fact that materials are not continuous and also heterogeneous. At every point, the material is different. Okay. So let us just quickly wrap up this. So tell me, if I had two springs with two different spring moduli, elastic moduli, and two different failure strengths, tell me what will be the overall K1 plus K2? K1 plus K2. So, but up to what point? So, huh? So now I keep adding the load. Okay. So it will be K1 plus K2 up to So when it reaches F1, will the first spring break?
Yes.
Sorry? It won't fail at F1. So how do you do that? So for this, you have to look at because now both of them are extending by the same amount, you have to look at the failure length, failure deformation. So that means you have to look at this one. So this is, supposing this is E1 and this is E2. When it reaches E2, anything more than that, the first spring, the E2 spring will fail. Okay. So let me just draw it a little bit. Okay. So what will happen is, first, up to the point where it reaches E1, up to the point where both springs are extended to E1, both springs will be resisting the load and the modulus will be K1 plus K2, right? Then what will happen is at that point, suddenly this one will break. I don't know which one is one, let us say this is 1 and 2, so one will break. Then if I continue to load it, what will happen? If I continue to keep this thing, and then it will reach E2, but at what slope? Now K1 is gone, it will only be K2. So suddenly the slope will change and it will go up to E2, and then what will happen? Then even that will break. Got it? So now imagine instead of just 2 springs, I have many springs. What will happen is I will get a real force displacement curve that will look like that. If I had many springs, 1000 springs, if I have, it will look like that. By the way, that is a much more realistic description of how materials behave than just this straight line. So by having straight line elements, we are now able to get a much more realistic distribution of the description of how the material behaves. Yes.
Sir, yes, sir. So let's take the 2 springs. So to get it to E1, so to get the extension to be E1, the force must be E1 into K1 plus K2. That is E1 into K1 plus E1 into K2. After that, the first spring breaks. So now only K2 is there and it is E1 into K2. Sir, so but then since the force you have applied, won't it just rapidly increase the extension because the force is still applying and it will rapidly increase the extension and the spring will break, the second spring will just break just after that.
Okay, good. So good. So there's a important question. So here, by the way, there are 2 kinds of loading methods that materials undergo. One is called so-called displacement control. So how much it is going to extend, that much force, whatever force. So the force, if it has to reduce, it will reduce, but you want to control the displacement in which it will move. Okay, that is one sort of practical examples of situations. In another case, it will be what is called force control. That means it's like, you remember we hung a weight. You keep adding weights to this thing. That means you keep increasing the force and suddenly boom, it will break. That is called force control. Both are practically possible. Force control is more common, you are used to it, right? If you sit on the table, your friend also comes and sits on the table and so on, boom, it will break. That's force control. Okay. Whereas there's some possibilities of displacement control also, even in real materials, where if you had a frame which is much stiffer than your material, and that frame is moving because of some other reason, either a thermal reason or some other reason is moving, then it's called a displacement control. That means whatever force it needs to apply, it's able to apply because that frame is so much bigger. Okay, so both are equally likely. And the answer to your question is, in this case, we are considering displacement control. That's easy to think about.
So which will be more, which kind of loading will be more common in practical
scenario? You have to look at your actual situation and decide which it is.
Yes, sir. But which will be more common generally?
See, I would say force control is, or both. I would say both are equally likely. For example, if I want to model how the floor is in relation to me, that is, I am applying a force on the floor. If I want to model my body, I will apply displacement control because the floor is so much more rigid than me. It is just going to support me. Even if somebody comes and sits on my head, that floor is going to be at the same location. So that is, displacement is known. So those are all displacement control thing. But in some case, if I standing on a trampoline or something like that, or you're trying to model the deformation of this flexible foam, then it will be force control because you apply the force, it will deform because the force will be different. Because of that, it will be. So both are equally likely. Yes.
But then if you go till E1 and then it will break, but then once you release the force, it will from the next time when you apply a force again, it will only go with K2, right?
Excellent. Very good. Very good. Very good. Very good. So this is an intermediate state. So there is. So if you go now and if you unload it, okay, then how will it unload? It will unload with K2. Okay. Right? Yeah, it will just follow along the K2 curve. Right? So that is now, that means there's a certain amount of inelasticity. So it's no longer an elastic curve. Elasticity means you have to follow the same curve in loading and unloading, whereas here there is some permanent damage that has occurred. Therefore, it follows a different curve. Okay. So so this is a very simplistic model. So there might be some aspects which will not be exactly the same as what you would expect in real life, but that's okay. Yeah.
While we can imagine the object as multiple springs, how do we calculate the K value of each spring?
Excellent question. Very good, very good, very good. So the question is, how do we calculate? So this is a model. By the way, this is true with all models. You can only conceptualize the model, but there will be some properties that will depend on the actual material. If this is made of glass, you would expect K1 and K to be some value. Made of rubber, you'll have different K1 and K2. If it's steel, it'll be different, right? So that part, you should have a very systematic way by which I can calculate the K1 and K2. I have to have a systematic way. So the way I would do it in this case is, I would have to of course use real material curves. So a real curve of the material will have some curve like that. It'll be different. It'll look something slightly different. So then what I actually do is, these are some techniques in mathematics where I try to find out the error between the actual experimental data and my K1, and I minimize that error by something called a least squares method. Okay, so I find K1, K2 combinations. In one case, I'll go like this and it'll go like that. In another case, it'll go like this, and so there'll be different combinations of K1 and K2 which will minimize the error. Okay, so these are all things that they're called parameter identification. So whenever you come up with a model, the model will have parameters. There's a systematic way by which you have to identify those parameters. Good question.
Difference in K is because of the deformation inside the object itself. So can it be done like scanning the body?
Very good question.
So identifying where the deformations are and accordingly adjusting our standard K value to those values.
Very good question. So his question is there some other way? So here I am doing a bulk deformation. I am just taking this little bar and I am just pulling it overall and finding out how it overall extends, and from that I am trying to find some local model of the K1, K2 and all that. But he's asking, can I do it even more in some other way in which I can literally get those detailed properties? To be perfectly honest, there are some techniques that are being developed. Those are still quite, those are called some non-destructive testing. For example, there's something called CT scanning technique, computed tomography. CT means is an X-ray. So people do an X-ray of objects and find out how the density is varying from point to point. Using that, they try to see if they can back calculate. It's okay, it doesn't work that well, it's very complicated. Sometimes you wonder whether it's worth the time. Okay, so if it walks like a duck and it quacks like a duck, it is a duck in my view. So don't worry about whether it's literally got the 10th feather that it should have or not. Overall, it kind of looks like a duck, it's okay. So lots of times in engineering we do that. We try to do that. Second technique that people use, another thing is they use something called DIC, digital image correlation. So what they do is they take a body and then apply a load, and before that they'll spray a paint on it. Okay, in dots, random dots. When you apply the load, these dots will all move. by correlating the current position of the dots in the previous position, you can actually get information about where it's weaker and where it's stronger and so on. There are all these very advanced techniques. People are right now, this is in 2023, people are working with techniques to try to do so. But I hope I gave you a flavor mainly about the fact that there are still such fundamental questions that we're literally going back to 11th standard springs and masses. By the way, okay, I've done this with static springs, but of course, I also immediately think, why not put a small mass here? And in fact, put more springs, put them in series, parallel, all of that, and put springs and masses, and then you'll get your spring mass systems that you also studied. So with that, you can get more richer description of the material behavior. So what will happen is, because these things are vibrating when I'm pulling it, that vibration itself will cause some local damage to accumulate, and that will give a better description of the overall fatigue life and so on. So there are all these aspects. We sit down, and that's what we do joblessly day in day. I get a PhD student in my office. I don't let them go till we like sit down. We have a nice big blackboard. We keep working it out and seeing what we can break our heads against, right? So that's the sort of very exciting thing. Now there's how to bring in temperature effects. How to, if temperature changes, how does that change? Okay. And of course, this is, by the way, this is also a model only. This is by no means, there is nothing that is true or exact in my view. Everything is a model. The moment your model stops working, then you may have to either go scratch, throw the whole thing out, work with something new, or see if you can make some modifications and so on. So the continuum approach, which Euler, Cauchy and all did for 250 years now, it worked very well. So if you tell me, oh, I'm leaning on this table, how much will it deform? If you ask me that question, I will say, okay, take a continuum and boom, boom, just set out the equations like Euler and Cauchy did, solve the damn thing, and I can tell you a good estimate of how much it will deform. For that question, that answer is beautiful. But now you tell me, hey, the thing broke, where will the crack grow? Will it go like this, or will it go like this, or will it branch? What will happen to it? Then there I have to throw up my hands and say, look, the method given of a continuum is no longer any good. Tell me what you can do better. Okay. So good. So I hope I did not bore you too much. I hope you got a nice flavor for what the exciting things that we do, and what keeps us excited at night. And like, I couldn't sleep last night. I'll be sitting and like trying to solve some, and these are so fundamental, you know, I can literally, probably if you come for a project, I can give you this problem and you can sit down and work it out for me. That's that simple, really. What is there? Now tell me what aspect of this calculation you cannot do. And by the way, if you can't, you can, of course, nowadays you have to know how to write a code. Some of these things, you know, instead of if you have 2 springs, I gave you 150 springs, you can't sit and calculate all 150. There you write a small Python code or a MATLAB code. You can do it. It's not a big deal. So literally, these are some fundamental techniques which are accessible to anybody and everybody. So all the physics that you're learning, don't forget it, because who knows, tomorrow you will apply such a fundamental principle in some electronic circuit or something else, right? Good. So that's all. Question? Yes. Yes. General questions are welcome.
Computer science and technology have improved so much in the past years. But when it comes to civil engineering, don't you think that our systems were better with the structural stability? It still stands, but nowadays the buildings, you know, they just crack open and the waterproofing, like nothing is. I mean,
Doesn't seem to be doing as good as possible. So
all the knowledge go?
where did the knowledge go? Very good, very good. Excellent question. I really like that question. So, so you would expect that we would be building much better stuff now than 5,000 years ago, and yet you can see a pyramid standing, but you can't see anything. And no building even 100 years old is standing. What is going on? So here there are 2 competing things. That the pyramid was damn expensive, that only one pharaoh could build it like every 1,000 years or something. And here today we want everybody to have a house. So because of that, you try to cut corners and make it as cheap as possible. And because of that, there is a certain loss. So you don't mind having a house for 70 years, let the next generation take care of itself. So I'm just this thing. So that is a shift in the attitude. I wouldn't say shift in the knowledge. Tomorrow, if I had to, if like a civil engineer had to build a house which lasts for 500 years, I'm sure they can do it. The only thing is they have to put factors of safety of, right now they probably put 1.5 as a factor of safety. They'll just put 3, 4, then they'll be able to build. That's not a problem. But another question, actually, nice question about, nice aspect of what you said was, in some areas, we seem to have gone ahead very well in our technology. But some, I would agree with you that we are still a little bit behind in our technology, or at least it's not growing as fast. An example I would give you is energy storage. Okay, so if you look at computing power, every 2 years, Moore's law tells you double the computing power every 2 years, like amazingly, right? Whereas if I ask you for energy storage solutions for a medium-sized factory or a small town, I want to store. So supposing I put solar panels and collect energy, but at night I will not get any sunlight. So I need to store it even for night. Actually, I don't mind putting double the number of panels. No problem. Store half that energy. But right now there are no good means of storing that kind of quantity of energy. We are very good at like storing like in our laptop and this thing, but that also I would not say is very good because we all discussed environmental costs are there. But certainly if it goes to a size of a medium factory, large factory, nowadays Google is trying to build these huge lithium farms, right? Which is very bad. I think environmentally it's very bad. So there's got to be some other way. So some fields do, just to answer your question much broader than you have, some fields do not progress as much. I guess it's probably because, I don't know, I think there's more constraints in the form of the materials that you are allowed to use and so on. There's a much more difficulty in being nimble in your changes. See, if I made a new algorithm in my computer or my cell phone and it failed, no problem, one more update. It's not what as Microsoft would say, it is not a bug, it's a feature. It'll convert it to a feature and say, no, that's what's supposed to happen. Blue screen of death, no, it's supposed to happen, right? So that's what they will tell you. But I can't do that if it's something like in civil or in aerospace or something. I can't just put some material there and cross my fingers and hope it won't fall off. I can't do that. So because of that, the time scales of those modifications will be much slower. Yes.
So I was actually talking about this with my roommate. I think there's also a little bit of survivorship bias. So for every building that stands, there are probably 5 or 6 that have failed over the years.
That's a good point. So what he's saying is the 5,000-year-old building that stood is significant because it stood. There might have been maybe 100,000 buildings that have collapsed already. That's true. That's a good point. But the fact is, the fact is at least one stood means that it is possible to actually build. That is, it is within the realm of possibility. That's all we're saying. Yeah. One question from here. No. Yes.
Also, like for the best of our buildings, we haven't had 5,000 years to test whether the best of our buildings will stand. So it may or may not.
May or may not. Probably won't, right? It probably won't. It won't. It may not. So, I mean, I think we can guess. You're right. We are not saying, but I think we can guess that we are not building any buildings which will last more than. See, in building technology, there are these. You have to guard against 100-year storms, 250-year storms. That is a storm which is so severe, but it happens only once in 100 years. So there's a 50-year storm, 100-year storm, 250-year storm is one very severe, like almost like a big tsunami and a huge storm. So if you look at that, I don't think we are building even to that sort of thing. So we know that. Yeah, your question?
So like there's, I think there are like recent discoveries of self-healing polymers.
Yes,
So
yes.
in that case, like how do you calculate the like stress and
Very good question. So now, in fact, the reason why I gave you, of course, a very simple example of fatigue failure and so on in like a normal steel bar. But I am also very interested in very novel materials. People are building materials constantly. There's something called shape memory alloys, materials which can remember your shape. Okay, look up some YouTube videos on shape memory alloys. Very interesting. Okay, these are almost as strong as steel, but will deform like rubber and will go to. You can make some nice shape and you can stretch it out, put it in a hot cup of water. It will come back to the original shape. Okay, very interesting. So I am interested in those sort of very novel materials, and one of those materials is called self-healing polymer. So if a crack forms, as the crack is growing, it does stuff that will cause the crack to again close up. Very important and very high potential for safety in aircraft industry. Unfortunately, those are just polymers. In the real engines and all, you can't use it, unfortunately. But I am interested in certain questions that are related to that. For example, even in steel, can I put some particles? What should be the size and distribution of particles even in steel, such that in case a crack forms, it will just get attracted to one of those particles and get stuck there, remain there. It will never grow again. So it may not have to heal, but at least it will not grow till it fails completely. So there are possibilities of that. But to understand or even model that right now, there are not many opportunities. So I'm very interested. I gave you only a small flavor, but there are a lot of such novel materials which I work on, right? So, any other questions? Yes.
no? So my doubt was like, how do you calculate this sort of stress for those sorts of material like self-healing polymers?
Yeah. So how do you even calculate these properties? So it's not a simple thing. We have to come up with. So we have to look at what are the most critical properties that we want to mimic. Okay. So overall, supposing my load displacement graph for a self-healing polymer looks in some fashion, I have to make sure I first mimic that overall load displacement. Then I have to look at, and for that, what sort of micro scale properties should I give, such that I'll do that. So should it be dependent on the amount of extension? So some springs, after they extend too much, I can start making it stiffer. Like supposing something extends a lot. Usually these self-healing polymers, the way that happen is when they break a lot, that is, then there'll be gels of different kinds, different chemical compositions in two different pores. If they break a lot, these two gels will meet and then they'll become one solid mass. So something like that. So I may have to use that physics and build it up such that my spring is, as it extends too much, the stiffness suddenly starts going up. Okay, things like that are possible. So it will be a non-linear spring. So yeah, those are the possible. Yes, question.
So this question might be a bit out of place.
No problem, nothing.
You know how you talked about the scientific process and how like needs are very important to like acknowledge.
For the engineering part.
Yeah. So do you think the main difference between one of the main differences between science and engineer products and art would be the lack of a process?
Lack of a process. Good, very good question, and I think I'm stepping out of my comfort zone in my answering here. But you're going to finish up your question. Is there anything else?
Yeah, because artists don't really recognize needs. They just put.
That is true. Actually, I have a colleague in my department, Professor Rajni Krishnan. She's a very good artist. She's a sculptor, and she teaches a course on these lines. How art, what is the role of art, and what is the artist trying to do? She has her own sculpting lab and all that. She builds beautiful sculptures and so on. So she does talk about this. We've discussed a little bit about this. So my answer is second hand. Let me put it. So broadly speaking, yes, you're right. An artist is trying to express themselves. So it is in a sense not looking for a societal need at that point. But there is, by the same token, it is also somehow seems to be in line with the societal, what the society appreciates as an art. So in other words, it is very difficult for an artist to go completely like in a tangential direction and come up with something that is so outre, something that is so out of the left field that people don't appreciate it. In such a case, it will be lost. Okay, so if you want it to strike a chord, at the end of the day, artists, even though they're doing it for themselves, they want it to strike a chord in this thing. So she's doing some research on it, very nice research. So she looks at different societies, not just art, she looks at the various other aspects of how that society, what that society values, and sees if there is some commonality between the art it produces and what the society values. For example, to give you an idea, the way Indian society looks at color and the way, say, a Western society looks at color seems to be very different. The kind of the colorful dresses that we wear versus the colorful colors that is used. So she is looking at what could be causing that thing. Similarly, in sculpture, things that we value in sculpture seems to be very different from, say, an ancient Greek sculpture. So she's looking at those aspects. So there's lots of good stuff. I didn't give you an answer. I only said that there's stuff out there. I don't know much about it, but it's a very good question. Okay. If you really want to find out a little bit more, please feel free to talk to Professor Rajni Krishnan in my department. If you look up our department website, you'll see her name. You can just, if you have any question, you can just write to her. Very knowledgeable lady. She's very, very knowledgeable. I really appreciate her inputs. Okay. That's all? Okay, great. Thank you so much for your questions.